And I just want to briefly talk about work and energy so that you have an understanding of it, so that if you take another physics class, like either later in high school, I don't know, we might offer a DP physics class, or in college, that you've got these notions that you've seen at least once. Okay, so when we talk about work, we're talking about a force acting over distance. All right, so work is force acting over a distance causing a change in position. And just to be super clear about what that means, like work is force over a distance. So here I've got my lovely Wonder Woman mug, and I don't know if you've noticed, but over my left shoulder there's a Wonder Woman lunch pail. That's all for my wife. That's her role model, Wonder Woman. So if we lift this mug, we're applying a certain force through a distance, and so we're doing work, right? So these two things are critical to work happening, a force over a distance. Now that distance can be vertical, distance can be horizontal. It can be anything within these three dimensions, okay? I can push against something, all right? And as long as it moves, I'm doing work. So I can push against this rolling chair. I push against it, it moves, I'm doing work. But if I push against the chair and it is not moving, I'm not doing work. Right? According to physics, there has to be both a force and a distance. Alternatively, if I'm rolling a ball, I am doing work when I am moving it with my hand, but as soon as I let it go, there's no work being done because there's no force. That's all momentum. So you have to have that force and that distance at the same time. Something else I want you to be familiar with is impulse. Is that force acting over time causing a change in momentum that is referred to as an impulse. And that an example of that was when I was throwing the ball. I was imparting a force over time and causing that change in momentum. But impulse and work are different things. Work is much more important. I want you familiar with that. So we see down here, the definition of work equals force times distance. And the standard units that we're going to use for work are joules. That's how you say that, that's a joule. A joule is equal to 1 Newton times 1 meter. So if you want to get work back into joules and you're measuring in centimeters, then you have to convert those centimeters to meters. And we know that we've been measuring force in newtons, so that's not tough. But 1 joule is equal to 1 Newton meter. And that is an actual thing. You can say Newton meter. I gave you a couple of examples of work and some non-examples of work. Does work have direction? What do you think? Does work have direction? Is work vector or scalar? That's what I'm asking. What do you think? Is work a vector or a scalar? Does work have direction? The crowd went mild. Nobody even wants to hazard a guess. You do need to take notes on this, Aisha, yes. So, yes, it's a vector, Victor. Yes. These are work has direction. If, now, and this is kind of the giveaway, right? If we apply work at an angle, then we have to include cosine of theta, cosine of the angle, right? If we simply apply work, a force, if work happens between a force and some object, and that is, the force is applied at the same angle as the direction of the movement, then everything is fine and you don't have to include that cosine theta. Work equals force times distance, right? In the case of like just pushing an object and you're pushing it directly and the object is moving in the same direction that you're pushing, then you do not have to include the angle. But if we have like a string attached to a box, a 30-kilogram box, and we have an applied force of 10 newtons, in order to calculate the work that is happening here, because this box is going to move along the ground, we need to include this angle, this 30-degree angle. All right? So this angle will help us calculate how much work is being done along this axis. Even though our applied force is here, that's when we need to include that cosine theta. All right? And this is just introducing this piece, understanding how you would calculate if you have an angle between the force and the distance traveled. All right? And that's all I want to say about work right now. What you need to remember, work equals force times distance, and that the units are in joules. Newtons and meters make up joules. Any questions about work? And again, the optional assignment is that activity sheet about work. It's a PDF. I apologize, I didn't make it into a Google Doc, but that's a PDF. Now, I want you moving to the activity sheet on energy pie charts. That's on number 95. To make these pie charts, you can write them on a separate sheet of paper and take a picture. You can insert a drawing. So you can make a circle, and then you can make, oh, that made it huge, didn't it? And then you can make lines within that circle to represent the different parts of the circle. Don't worry about it being geometrically or mathematically accurate. Remember, that's not what we're concerned about. We're just showing proportions. And then you can put your text box in here. So you could say elastic potential energy, for example. And the beautiful thing about making these drawings is that you can copy and paste the drawings and then just change them for every successive drawing that you want to make. So it can make your life a lot easier, but I will I am perfectly fine accepting something that you handwrite. So let's go through number one to make sure that we're all on the same page, that you all understand what I'm expecting of you. Whoops. So we're on number 95, activity sheet, energy pie charts. And number one, a ball is held above the ground and then it's dropped so it falls straight down. All right, we are restricting our analysis to the ball moving in the air before it hits the ground. So how many pie charts do you think I want you to make for this? So this third one, I do want you to make 3. This third one, I want you to make for the instant before it hits the ground. All right, it's moving in the air. Don't consider it as having hit the ground at this point. What do we see happening to the velocity? What do we see happening to the kinetic energy? Yep, velocity and kinetic energy is increasing. So let's imagine this example right here, where the ball is at its highest point and its velocity is 0. It is not moving. So let's make the pie chart for that. If it's not moving, what kind of energy does it have? Y'all are really gonna make me hold this ball in the air.
Potential energy?
Yeah, great. What kind of potential energy is it?
Gravitational?
Absolutely. And that is 100%. 100% of the energy. Let me bump up this font here. Is gravitational potential energy. I like my favorite font. Okay, so I put the lines over on the right because I want to be able to reuse those lines. And I'm not interested in this looking pretty. I just want it to represent stage A, B, and C. And they're not labeled A, B, and C, but if you put them in order, I'll understand what it is. So my first pie chart, 100% is gravitational potential energy. It's not moving, okay? And another way of representing this is E sub grav. You do not have to always write it as this. It's fine if you do. Makes your life easier because that's less you need to write. But that would be E sub grav. Okay, so I'm going to, again, make my life easier. I'm going to copy and paste, Control C, Control V. And now we're going to consider the second piece. What does it have here in this moment? It just has fallen from being dropped. What does it have here that it doesn't have here? What kind of energy? It's very difficult to juggle just one ball. if it were summer, I'd be able to hear the crickets outside. I think I can almost hear the snowflakes. Hey, great, kinetic energy. Excellent. So there's some kinetic energy. Most of the energy is still this gravitational potential energy. But let's again be lazy. I'm going to copy and paste this text. Already got text, might as well use it. So some of this is kinetic energy. That is E sub k. You notice I'm not concerning myself about colors. I'm not worried that the text spills over. I'm just making sure that I'm representing the fact that some of the energy has been converted from gravitational potential energy into kinetic energy. Now, the instant before it hits the ground, that moment right before it hits the ground, how am I going to represent that?
It's gonna have a lot of kinetic energy and very little gravitational energy.
Perfect. A lot of kinetic energy and the tiniest little bit of gravitational potential energy. So just to emphasize how tiny that is, there it is. Little E-grav and a lot of kinetic energy. There is no right answer to this. You could make this slice a little bit bigger if you wanted, right? I'm not going to tell you that's wrong. You could even drop it down all the way to 0. You could just be like, well, that instant right before it hits, it's got practically 0 gravitational potential energy. And I wouldn't disagree with you, all right? Now, the moment where it's half and half is halfway through its fall. So if the ground is here and it gets released here, I'm trying to coordinate it in my screen here, then about halfway through is when it would, half the energy has been converted from gravitational potential energy to kinetic energy. So that's when it would be half and half. But in this moment here, then there's just that tiny little bit of gravitational potential energy, and most of it is kinetic. Okay, so I would like you to continue through these. Again, you can write it down or use the drawing tool. And just to kind of give you some starters here, a wind-up toy has potential energy stored as what kind of potential energy? Excellent, elastic. This one it starts to get a little tricky, okay? 1, 2, 3, 4, 5. I want you to have 5 different pie charts here. Think about it this way. This is being thrown up in the air, this baseball. It has very little gravitational potential energy because it's very close to the ground. But in order to get up here, it has to have a ton of kinetic energy. So you will see a pattern start to develop here. But the relative proportion of kinetic energy at this moment is super high. And again, for this, you should have 5 charts. Okay, this is a super ball, so it has elastic potential energy. It's storing that energy as elastic energy. So make sure you represent that when it hits the ground. So I'm going to give you the rest of the time together to work on these. I'll be here for questions. I need a minute to get myself some more coffee, and I will be right back up. But start on these and enjoy some lo-fi hip hop.